Hello everyone. In this video, we're going to learn about inverse trigonometric functions. We'll start with a general discussion of inverse functions to remind you about what they are, and then we'll proceed with introducing inverse trigonometric functions. If you recall, a function is basically a rule that assigns to each member of a given set, such as the set A, B, C here, exactly one member of another set, for example, the set 1, 2, 3. And the keyword is the exactly. In other words, each input should have exactly one output. Now, it is not a problem if two inputs have the same output. That still qualifies as a function. But if one input goes to two inputs, like if one were to go to both 1 and 2, then it would just be a relation, but no longer a function. So a relation is any set of ordered pairs, any kind of association you create, but a function is a special kind of a set of ordered pairs where no two distinct ordered pairs within the definition of the function should have the first the first coordinate being the same. So both of these are indeed functions. However, we notice there is something different about f, which is the fact that not only does each input, these elements here are called domain elements or inputs, no two inputs go to the same output. So whereas this one, if you notice, both A and B have an output of 1. But in this case, not only does each input have one output, no two inputs have the same output. This makes f very special in the sense that it's reversible. In other words, if we ask about any of the output elements, which are called the range elements, where that element comes from, we could easily trace it back to its source. We couldn't do that here, for example, with 1, because we could say, well, it maybe came from A or B. We can't give a definite answer, but here we can give a definite answer, and that makes f very special and reversible. We call functions like f, where no two inputs have the same output, 1 to 1. And these functions, again, can be reversed, and that reversal creates a new function called the inverse function. We write it with this notation, f and a superscript of -1, which is not to be confused with an exponent. So f to the -1 does not equal to 1 over f, like it did in algebra. This is a notation for inverse functions, and the way you read it, you say f inverse. So what f inverse does is exactly send all the range elements of f to their domain elements. So it switches its domain and range with f. So what was the range of f becomes the domain of f inverse. And what was the domain of f becomes the range of f inverse. And notice the definition of f here as a set of ordered pairs. It's ordered pair A1, ordered pair B2, and ordered pair C3. Notice the ordered pairs that compose f inverse as a set of ordered pairs are the exact reverse. Ordered pair 1A, ordered pair 2B, and ordered pair 3C. And we already spoke about the domain and range of the two. So very simple concept, but very important. Make sure you understand it before we proceed. The domain and ranges that we saw in the previous page were functions that had finite domain and finite range. Most of the time in mathematics, we deal with functions like the ones depicted here that have infinite domains and infinite ranges. Of course, both of these graphs, this is the cubic function and this is the quadratic function, the reference quadratic function. Both of them keep going forever, so normally you can put arrows there, but even if they're not, it's understood that they don't stop where we see them stop in the graph. That's just because of limitations of technology and paper. Otherwise, they keep going ad infinitum. And notice that they both pass what we used to call the vertical line test in algebra, which basically means if you look at either graph, there is no vertical line that's going to cross it more than once. So what that means is that no input element, which we depict on using x elements from the x-axis, is going to be associated with two outputs. Therefore, they're both past the function test. However, notice that f also passes another test, and that test we call the horizontal line test. So what that means is that, as we said in the previous screen, not only does no input have more than one output, but also no two inputs have the same output. So that makes f here 1-to-1. So, but notice the quadratic function fails the horizontal line test. Here is just one here shown for example. There are many horizontal lines that will cross the graph of x squared more than once, which of course that means we have at least two inputs that have the same output. Notice both -1 and 1 when plugged into x squared will give you the same output 1. So this is not a 1-to-1 function, but this is a 1-to-1 function, which means this one will have an inverse, which we have depicted here. The inverse is actually the cube root of x. And they're going to play a very important role as we develop the concept of inverse trigonometric functions as well, these 1-to-1 functions, because essentially they're the only ones that are reversible. So once again, we start with an input x, a function f takes that and gives us the output y. Then if the f inverse, if it's 1-to-1 and the inverse function exists, it's going to take that output y and send it back to x. So this creates a very interesting kind of symmetry for us, because if we know that f of some value a is b, that means a is sent to b, we know that f inverse of that b element is going to go back to a. So what this means is that if f of a is b, we know that means that the point ab is going to be on the graph of the function f. And because f inverse of b is a, we know that that means the point ba is going to be on the graph of the inverse function. So this kind of symmetry is symmetry with respect to this special line, which is the 45-degree line, which we know is defined by the equation y equals x. All inverse functions, and remember, inverseness is a mutual relationship. It's not just f inverse, which is the inverse of f. F is also the inverse of f inverse. So all inverse functions have graphs that are symmetric with respect to the line y equals x. So here we show that beautiful symmetry that exists between these two inverse functions. In red we have f of x equals x cubed, and in blue we have the inverse function for f, which is the cube root of x. And as you can see, they're perfectly symmetrical with respect to the line y equals x, which plays the role of the mirror of, or axis of symmetry in this case. We normally reserve the name axis for the vertical or horizontal one, so here we just call it the line of symmetry. Now, as we mentioned, f of x equals, or in this case we call it g of x equals x squared, was not 1-to-1. But is all hope lost for this function, for example, x squared, to have an inverse? Actually, the answer is no, because what we can do is what we will show in a minute on the next screen. So here in the middle, we have the graph of x squared, g of x equals x squared. Notice that if I were to restrict its domain, in other words, let's say I were to look at only the inputs starting at 0 and going to the left. In other words, restrict myself to -infinity to 0. then if you notice, we do end up with a function here shown in red and called g1, which is 1-to-1. Notice if you look only at this red graph here, it does pass both the vertical line test and the horizontal line test. So this is called restricting the domain of a non-1-to-1 function to create a 1-to-1 function. Notice that with that restricted domain, it does get to have an inverse function, and this actually happens to be negative square root of x. In an algebra class, we've gone over this. You should probably know how to obtain it. But we could also restrict the domain by looking only at the non-negative numbers. Here we looked at non-positive numbers. We could have also restricted it to the non-negative numbers. So we're only taking the right half of the graph of x squared. And notice that that piece is also 1-to-1, and it will have an inverse, and this time the inverse is g2 negative 1 of x equals square root of x, the positive square root of x. And that's how we can take a function that is not 1-to-1 and basically create a 1-to-1 function out of it. Now, why is this important? You'll find out on the next screen. Okay, we're very familiar now with the graphs of sine and cosine depicted here. And if you notice, they both pass the vertical line test. There is no vertical line that would cross either one of these two graphs more than once. So they're both definitely functions. However, if you also notice, they both miserably fail the horizontal line test. In fact, the x-axis itself in both cases is a horizontal line that crosses these two graphs infinitely many times, right? So they're both as far away from 1-to-1 as you can be. Notice that if you go back to the previous screen, poor x squared was disqualified from being 1-to-1 because it had horizontal lines that crossed it only twice. But that is bad enough to disqualify it from being 1-to-1. Now let's go back with sine and cosine. Of course, there are many horizontal lines. In fact, infinitely many you can draw just between -1 and 1 that would cross it infinitely many times. So if we are to have any hope of defining inverse functions for sine and cosine, we better do some real intense restricting of their domains, and that's what we're going to do next. First of all, notice that there are many different parts of the graphs of sine and cosine that we could have restricted ourselves to, but the most convenient ones were just the closest ones to the standard origin location. So the domain that we restrict ourselves to for sine in order for it to become 1-to-1 is just the zone between -π/2 and π/2. It's also significant because in that interval, notice sine will achieve all the values between -1 and 1. All the different values, outputs that are possible between -1 and 1 will be realized and achieved just between those 2 points on the input axis. For cosine, the same interval would not work, but if we restrict ourselves from 0 to pi, notice cosine will also achieve all values between -1 and 1 during that interval of length pi. So this is our restricted sine function, which is 1-to-1 now, only within that domain. And this is our restricted cosine function, which will also be 1-to-1 on that new domain, restricted domain. So let's go ahead and look at how we can define the inverses now. So we'll start with the inverse sine function. It's also called the arc sine function. That's an older terminology, but you need to be familiar with it in case you see it. So the function we start with to find the inverse of will be sine x with the restricted domain from negative pi over 2 to pi over 2 as we mentioned, and of course a range of outputs from negative 1 to 1. Now the inverse function will be called the inverse sine of x. Again, remember, this is not an exponent, this is inverse function notation. And remember that they switch domains and ranges. We've depicted it here. Notice in red we have the sine function, which we're familiar with, from negative pi over 2 to pi over 2. And in blue we have the beautiful reflection of it, or the mirror image with respect to the line y equals x. Everything we said about inverse functions before and learned in algebra applies here as well. And notice that the domain of sine will be the range of the inverse sine, and the range of the sine function will be the domain of the inverse sine function. So inverse sine basically lives between negative 1 and 1. So here we have created a new kind of unit circle. Normally we use positive values, but remember, for inverse sine, we're going to be dealing with angles starting here at negative pi over 2, and then we go up here to pi over 2. So we've listed some of the main unit circle angles here. So we know that, for example, if we start with negative pi over 2, the sine, of course, is the y value of the ordered pair associated with that angle on the unit circle. So we know the sine is negative 1. So here we have negative pi over 2, and the sine of it is negative 1. But now this table works two ways, right? So that means if you start with negative 1, the inverse sine of negative 1 will be negative pi over 2. So basically, what you really need to understand is that when you see the inverse sine of x, that just means it's some real number between negative pi over 2 and pi over 2 whose sine is x. If you understand that, you've basically understood what we're talking about here with inverse functions. So notice that for example, the inverse sine of negative 1/2, right? So what are we looking for? We're looking for some angle here. Well, when we deal with radian measure, they're just real numbers. Or if you're dealing with degrees, they'll be angles. Same difference, we're familiar with it. So we can actually find the inverse sine of negative 1/2 as a radian measure or as a degree measure. So we're looking for some real number first. We'll deal with the radian measure first, between negative pi over 2 and pi over 2, whose sine is negative 1/2. Remember, sine is the y value. So when you look here, what angle do you see whose sine is negative 1/2? And of course, that's this one here, which is negative pi over 6. And that's basically all you have to do in order to find the inverse sine of a given number. Now, of course, if we were dealing with degree measures, we would have answered negative 30 degrees instead of negative pi over 6. But that's as simple as it is. So when you see the inverse sine of some number, you're looking for some angle in either radian or degree measure between negative pi over 2 and pi over 2, or between negative 90 degrees and 90 degrees, whose sine, meaning the y coordinate of the terminal side of that angle, would be negative 1/2, or whatever angle measure it is that you have in mind. So spend some time on this screen, look at these numbers. They should all be familiar for you. They're just coming from the unit circle we're familiar with. Notice we're going from negative pi over 2 all the way to pi over 2, and with pi over 2, for instance, we know that the sine is 1. So if somebody said to you, what is the inverse sine of 1? they're asking you what angle between negative pi over 2 and pi over 2, inclusive, of course, that means including negative pi over 2 and pi over 2, has a sine of 1. And of course, you know that that would be the angle pi over 2 itself. So that's how you calculate these inverse sine values. Let's move on and look at inverse cosine now. Recall that we restricted the domain of inverse of the cosine function depicted here in red to 0 to pi, so that we could make a one-to-one function out of it. Again, here you see the inverse beautifully depicted as the mirror image with respect to that mirror, which is the line y equals x. So the main function here, whose inverse we're finding, is f of x equals cosine x with this restricted domain, and of course the range being -1 to 1, because notice as you go from 0 to pi, notice that cosine takes all these values, the x values are the cosine, from 1 all the way to -1. You can see that it's a decreasing function because it starts at 1 and then slowly the values become smaller till they reach 0 and then into the negative region until we get to -1. With sine, it was the exact opposite. Let's take a look. Sine, on the other hand, starting with negative pi over 2 and working your way to pi over 2, start with its smallest possible value, which is -1, and the values keep getting larger and larger until they get to 0 and then into the positive zone until we get to 1. So you can see that inverse sine here depicted in blue will be an increasing function. So we've created a very similar table here, and notice it's running from 0 to pi. And again, the real important thing to understand is that when you're looking for the cosine, inverse cosine of some value, you're basically looking for some real number in radian measure or some angle in degree measure whose cosine, meaning the x value, is that number x. So don't be confused. We don't mean the same x here as we mean by the x coordinate here. So for example, the inverse cosine of -1/2 would be some angle between 0 and pi, right, whose cosine is, meaning the x value is -1/2. And of course, if you look at all the angles here, you can see that the one whose cosine or x value is -1/2 is right there, and it's 2 pi over 3. So that's a typo here. That should be 2 pi over 3. No, actually, that's not a typo because I forgot that I had changed this to positive. So the inverse cosine of 1/2 itself is, in fact, we're looking for an angle associated with an x value of 1/2, and that one is right here. So we can see that the inverse cosine of 1/2, the angle whose cosine is 1/2, would be pi over 3. So this was correct. No correction required. All right. Do notice that the range of the inverse cosine is from 0 to pi. That means the outputs of inverse cosine fall into quadrants 1 and 2. With inverse sine, if you recall, the outputs fall into quadrants 1, and as you know, this is quadrant 4. These are going to be important later when we're going to be doing certain calculations. So keep mental note of these facts. So as we look at the tangent function here, courtesy of Desmos, we can see that it also is as far away from being 1 to 1. You can see all these horizontal lines here crossing it infinitely many times. So we do need to restrict the domain. And it looks like it's going to be a very similar to domain to the one that we picked for sine, however with a subtle difference. Notice that tangent is not defined at negative pi over 2 or pi over 2. So when we restrict the domain, we're not going to use the closed interval from negative pi over 2 to pi over 2. We're going to choose the open interval from negative pi over 2 to pi over 2. Here, of course, we see the beautiful relationship between tangent with restricted domain from negative pi over 2 to pi over 2 in red, and its inverse, the inverse tangent function, which again are symmetric with respect to the line y equals x. This time, of course, once again, they switch domain and range. The domain for the restricted tangent function is from negative pi over 2 to pi over 2, again depicted in red. And the range, as we know, it takes on all real number values in that region. And for inverse tangent, the domain, if you notice in blue, the domain of that function is all real numbers, but the range, the outputs are bounded between negative pi over 2 below and pi over 2 above. And once again, notice that that's an open interval because this inverse tangent curve will never cross the pi over 2 line, nor will it cross the negative pi over 2 line here. So again, all you really need to understand is what the inverse tangent of x is that it's some real number between negative pi over 2 and pi over 2, this time strictly between negative pi over 2 and pi over 2, whose tangent is x. So that's why the inverse tangent of negative 1 is, notice, some angle between negative pi over 2 and pi over 2, whose tangent is 1. Of course, the only qualifying angle will be negative pi over 4 because its sine and cosine are equal but opposite. So their values when divided would give you negative 1. And of course, the inverse tangent of 1 would be pi over 4 itself because that's where the sine and cosine are equal. So when you divide them, you get 1. And a similar analysis to the one we just did for sine, cosine, and tangent will generate the three other inverse trigonometric functions for us. These we will rarely use, and we're going to find very soon that we'll be able to do computations involving these using the first three inverse trigonometric functions. But the most important thing to keep in mind is these quadrants of their outputs, because these will be important when we do calculations and we're trying to calculate some of these inverse values. So we'll summarize all of this in the next page so that we will have it handy for us. So I put these in a different order than most textbooks do because I think the most important thing is to try to remember these output quadrants when it comes to computations later on. So notice that inverse sine, inverse tangent, and inverse cosecant all have outputs between negative pi over 2 and pi over 2 essentially. Notice that with inverse cosecant we have to exclude 0, but essentially it's the interval from negative pi over 2 to pi over 2 excluding 0. So all three of those have outputs in quadrants 1 and quadrant 4, and the other three, inverse cosine, inverse secant, and inverse cotangent, will have outputs in quadrants 1 and 2, which we're going to need to remember. Those go from 0 to pi, if you recall. All right, in this first example, we're going to be looking for the inverse sine of negative square root of 3 over 2, and we want to give the answer in both radian and degree measures. So of course we know that for inverse sine we're going to be looking for some angle in this interval from negative pi over 2 to pi over 2 whose sine happens to be
negative square root of 3 over 2. Remember that when you're looking at the unit circle, the sine corresponds to the y coordinate of each of these ordered pairs. And we can see that the angle for which the sine or the y coordinate is negative square root of 3 over 2 is right here. So it corresponds to negative pi over 3. So we can say that the inverse sine of negative square root of 3 over 2 equals negative pi over 3. And of course, since it contains a pi, to convert it to degree mode is very simple. Just replace pi with 180 degrees. And remember, this only works if the radian measure you're dealing with has a pi in it. Then it's very quick. Just replace the pi with 180 and you end up with negative 60 degrees, as we can see here in this graphic. So it's also going to be negative 60 degrees. Remember, it's very important to understand that you need to look in this region from negative pi over 2 to pi over 2. Sometimes the students make a mistake of finding the actual positive angle that corresponds to that y value by going around the circle and stopping here in a counterclockwise manner. So you want to prevent doing that, avoid doing that, and you want to make sure you're looking between negative pi over 2 and pi over 2. And that's all there is to this problem. This one is actually going to be quite quick, as you probably know, because we just put these here for reference. But we're looking, when we see inverse cosine of 2, remember what that means. That means some angle between 0 and pi whose cosine, or whose x value of the associated sign on the unit circle, is 2. Of course, we know that the maximum possible value for cosine of any angle is 1. So we know right away this one does not exist. So no such real number or angle if we're looking at it in terms of degrees. All right, make sure you understand that it's subtle and important. Okay, so for this example, we're going to find the inverse cosine of 0, and we want to find it in both radian and degree forms. And notice that for inverse cosine here, we're going to be looking for some angle between 0 and pi, as depicted here, whose cosine is 0. Now, of course, we also want to find it in degrees, so 0 to pi or 0 to 180 degrees. And of course, as you know, if we're looking at the unit circle here, or part of the unit circle, the top half, then we know that the x value of each of these ordered pairs corresponds to the cosine of the angle whose terminal side happens to fall at that location. So in this case, when we're looking for an ordered pair whose x coordinate is 0, we find that there's only one, and that's right here at pi over 2. So that's how we know that the inverse cosine of 0 equals pi over 2. Of course, that's in radians, and we don't need to write anything, because when we don't write any units, automatically it means radians. And we also want to find it in degrees, and of course we know that pi over 2 corresponds to 90 degrees. So this is in radians, and we can also say the inverse cosine of 0 is 90 degrees. And that's as simple as that can get. Always remember, when looking for inverse cosine, look for some angle in that zone with the cosine that you are looking for. And that's how you do those. All right, so here we want to find the inverse tangent of 1, and we want to provide the answer in both radian and degree measures. So inverse tangent of 1, as you know, is some angle between negative pi over 2 and pi over 2. That's where the outputs of inverse tangent exist, whose tangent is 1. So, as you know, there's only one angle that will qualify here because that's the only angle whose tangent is positive 1 in this region. This one may be tempting, but as you know, the inverse tangent here is negative 1. The tangent here is negative 1. So the only one that qualifies as having an inverse tangent of 1 is going to be pi over 4, which, as we know, is the same as 45 degrees. In case you forgot how to convert those, you just go pi over 4 times, you're going to want degrees up here and radians here, so we use this unit factor because the top and bottom are basically representing the same quantity. These cancel out, and 180 over 4 is 45, so we get 45 degrees. All right, so that's how you do that one. Okay, for our next problem, we're going to calculate an inverse secant or arc secant. But before we do, let's understand why we don't really need to use those functions and we can use another function instead. Like, for example, let's look at y equals inverse cosecant of x, right? So we know what that means. That means that the x must be the cosecant of y, just by definition of what inverse cosecant means. And of course, we know that cosecant of y is the same as 1 over sine of y, right? So if we cross multiply here, we get x sine y equals 1. So sine of y equals 1 over x. So what does that mean? When we say sine of y equals 1 over x, remember there's another way of saying that. That means the inverse sine of 1 over x would be y. So, but remember what y was, right? Y is the inverse sine of 1 over x, and now we end up with inverse cosecant of x equals the same y. So in order to calculate inverse cosecant of a number, we can just basically calculate the inverse sign of the reciprocal of that number. So this is why we can do away with having to use that, because most calculators you're going to find don't have that anyway, in case we're dealing with an angle which we can't easily find the inverse cosecant of. We have to know this trick in order to use most calculators. All right, so, and of course this is going to be true as long as x is not 0, because otherwise this argument is going to become undefined. Look, we can do that also for inverse secant, for example. Let y be the inverse secant of x. That means by definition that x is going to be the secant of y. So if we replace secant of y with 1 over cosine y, we get x cosine y equals 1. So cosine y equals 1 over x, which again, by definition of what inverse cosine means, tells you that y must be the inverse cosine of 1 over x. And y is also the inverse secant of x, so those must be equal. So instead of calculating the inverse secant of a number, we can just calculate the inverse cosine of its reciprocal, again as long as x is not 0. Now here we have y equals inverse cotangent of x, and we do the exact same thing. So that means x must be the cotangent of y. So x equals 1 over tangent y, cross multiply, you get x times tangent equals 1. So tangent of y equals 1 over x, which again by definition means y must be the inverse tangent of 1 over x. So we can see that y is this and y is also equals to that. So this and this must be the same. So that tells you instead of calculating inverse cotangent, you can calculate the inverse tangent of the reciprocal. So now we'll look at an inverse secant problem. All right, here we want to calculate the inverse secant of 2. So if we recall we know that the inverse secant of 2 is the same as the inverse cosine of 1 over 2. Let's recall what we just did in the previous page. See, the inverse secant of a number is the same as the inverse cosine of its reciprocal. So this is safe as long as you do keep in mind that we are computing this quantity. So when it comes to the restrictions as far as the outputs, we need to be looking for this function. It just so happens that inverse cosine and inverse secant have the same intervals that they work with, of course, with the exception that inverse secant is not defined at is not going to have an output of pi over 2. So here we're looking for so for all practical purposes right now we can just worry about this. So we're looking for an angle between 0 and pi whose cosine is 1/2. And of course, cosine is the x value. So as we look in here, we can see that the angle whose cosine is 1/2 is pi over 3. Remember, the nice thing about the unit circle is that you really only need to know the values of one quadrant. The other ones you can get by just adjusting the signs. So there's not a whole lot you have to memorize. And of course, two of them are just 1, 0 and 0, 1 anyway. All right, so that's all there is to this one. So we want both radian and degree measures. So it's going to be pi over 3. I know that I showed you the shortcut of multiplying by 180 over a pi, but when there's a pi in the expression you're trying to convert to degrees, there's a quicker method. You can just replace the pi with 180. So we get 180 degrees over 3 because those pi's will always cancel out, right? So 60 degrees. So the answer basically pi over 3 radians or 60 degrees for the inverse secant of 2. I want to remind you of this warning I gave you earlier. Remember, inverse sine of x, that does not mean this expression. These are not the same thing. People make this mistake because, of course, if we have, for instance, sine squared x, that is in fact sine of x squared. But remember that the same logic does not work with this inverse notation. So it's neither this nor is it that. So be very careful, and this goes and it applies to all inverse trigonometric functions. All right, for this next one, we're looking for the inverse cosecant of -5. So as you know, we can compute inverse cosecant of -5 by just basically using the inverse sine of the reciprocal of -5, which is -1/5. Now this, as you know, is not one of our nice unit circle angles. That tells you we're going to need a calculator here. So let me bring one up to help us out. All right, so here we're going to get help from this wonderful calculator from HP, which is generously provided for free. It's called HP Prime Graphing Calculator. So basically, we're going to calculate the inverse sine of -1/5. So we want the answer in both radian and degree measures. So let's go ahead and see what mode we're in first. You always want to check that. So I noticed that right now this calculator is in degree mode. So I can go ahead and find the radian measure first, just because those are more commonly used. So I'll go ahead and enter shift sine. Notice HP uses kind of the old arc sine notation. And we're just going to type in -1 over 5, and then we can hit enter. So there is the answer in radian mode. So the angle between -pi over 2 and pi over 2. Notice that both inverse sine and inverse cosecant are defined in that same region. So let's see. All right, these screens can be very touchy. Here we go. So all right, so we know the answer in radian mode, and we can just copy it and use it. Now we could either sit there and convert that to degrees by, of course, multiplying by 180 over pi to get that answer. Or what we could have done is we could have gone back into our settings and we could have changed it to degree mode and then bring that back in and compute it again. And of course, it'll give us exactly the same number. So you know, there's no preference of one over the other. You know, they seem to be almost the same number of steps involved, you know, to do it. So anyway, that's how you go about doing a problem like that, which cannot be obtained directly from the nice values associated with the special triangles, 30, 60, 90, or 45, 45, 90 triangles. All right, we're going to now look at inverse cotangent of negative 0.3456. And we know that we can write that as the inverse tangent of negative, the reciprocal of that, so negative 1 over 0.3456. All right, this is one of those that you really have to be careful with, because notice here for inverse tangent, it gives you outputs in quadrant 1 and quadrant 4. But look down here at inverse cotangent, its outputs are in quadrant 1 and quadrant 2. So sometimes when we obtain a result for this, if it's in quadrant 1, we're good to go, because both of them are defined, have defined outputs in quadrant 1. But if our output happens to come out when we do it with inverse tangent, and it happens to come out in quadrant 4, then we have to adjust the answer so that we get the quadrant 2 version of that answer. So let's go ahead and compute that on the calculator to see what we end up with. All right, notice that this time we want the answer in degree measure. So we're going to go ahead and make sure that we're in degree measure. I believe we last put it in that mode. Yeah, so we're in degree measure already. So now we're going to go ahead, oops, that went to radians, let's see, degrees. All right, so choose, all right, so we can exit that now. All right, now we're going to go ahead and type inverse tangent of negative 1 over 0.3456. Okay, so we get that. Now let me go ahead and bring in a unit circle. All right, notice that the calculator is giving us negative 70.9 degrees approximately. We were in degree mode, remember? Now, of course, remember when a calculator gives you an inverse tangent, it's going based on this range. So it's giving you a quadrant 1 or quadrant 4 answer. Of course, because it's negative, notice that it's giving us a quadrant 4 answer, but look down below and you will see inverse cotangent needs to be either in quadrant 1 or quadrant 2. So we're going to have to get an angle that is associated with negative 70.9, but in this quadrant, because that's where cotangents are negative. Because remember, after all, when you're looking for the inverse cotangent of a negative number, That means you're looking for an angle whose cotangent is that negative number. And of course, that angle is going to have to be in here because that's where cotangent is negative between 0 and pi. So basically what we need to do is we need to take this angle that the calculator generated for us, and we need to go ahead and add a half circle to it, or 180. So plus 180, and that will be the angle that you're going to want to provide as the answer. So 109.1 degrees approximately. So be very careful with those and be aware of what output the calculator is giving you and what output you're actually looking for. Because in the case of inverse cotangent and inverse tangent, that's particularly where you have to be careful because they have different range quadrants. Okay? All right, so let's go ahead and look at another one. All right, we're back to one where we need an exact answer because this is going to be associated with one of our triangles. So it's inverse secant, so of course we're going to use the inverse cosine. So, and the nice thing about inverse secant and inverse cosine is that we don't need to have the same worries as what we just had in the previous problem, because they basically have outputs in the same quadrants, in quadrants 1 and 2, inverse cosine and secant, so right in here. All right, so this time we can just safely say inverse secant of 2 radical 3 over 3 is equal to the inverse cosine of the reciprocal of that, which is 3 over 2 radical 3. Now, you may not recognize this, but once you rationalize it, you will. So let's take a look at 3 over 2 radical 3 and go ahead and rationalize it. As you know, that means we're going to multiply the numerator and denominator by the square root of 3. So notice that we end up with 3 radical 3 on the top, and down below we get 2 times 3, of course, because square root of 3 times square root of 3 is 3. So now we notice that we can cancel out the 3's, and this should look much more familiar to you now. So it's square root of 3 over 2. So notice this is the same as saying find the inverse cosine of square root of 3 over 2. And remember, that just means find the angle between 0 and pi whose cosine is square root of 3 over 2. And of course, when you look in here, you can see that that angle whose x value is square root of 3 over 2 is right there, pi over 6. So we're going to say equals pi over 6, or we want both radian and degrees. So 180 over 6 we know is 30 degrees. So that's how you handle a problem like that. All right, here we have an inverse cotangent problem again, and it says to round to the nearest hundredths this time, and they're not specifying what measure to use. If it's not specified, go with radians, okay? So we're gonna start out, of course, by saying inverse cotangent of negative 0.008 is going to be the same as the inverse tangent of negative 1 over 0.008. So we're going to bring our calculator over, and this time we're going to make sure that we are in a radian mode. So we'll go to settings and make sure that we are in a radian mode. We choose that and then we exit out of there. So now we're going to calculate the inverse tangent of -1 over 0.008, and we hit enter. Okay, this is where we have to be careful again. Time for our unit circle again. Let me bring that over again. Okay, remember that we use the calculator for an inverse tangent, and that angle in radian measure is going to be in quadrants 1 and 4, between -π/2 and π/2. But we know that inverse cotangent has well-defined outputs between 0 and pi. So this time, again, we know that the answer we obtained here, let's go back to it, is -1.56. So we know it's somewhere in here, and we're going to add, let me show you exactly how much π/2 is. Let's calculate that real quickly, just so we know where -π/2 falls. So we're just going with negative. Okay, not that. Let's clear that. We just want negative. Let's see, it's not letting me clear. Okay, 1 second, little calculator problem. All right, we're back in action. I was hitting this, they're considering this subtraction, so we need to hit this one. So negative pi over 2. Didn't take my negative again. All right, it doesn't matter. Okay, so that's not what I want. I want this one. Okay, so the approximate is 1.57. And for the other calculation we had obtained, let's go back to it. I lost my screen there for a second. So second tangent of negative, this time we'll accept these for some reason, 1 over 0.008. All right, so notice that's -1.56, and -π/2 is at -1.57. So we're barely within this quadrant here. Of course, we knew the answer is going to be somewhere between -π/2 and π/2, because that's where inverse tangent outputs are. But just so that you know, you're in here. So if you want an angle whose cotangent is negative, you're going to be looking up here, exactly half a circle away. Again, this is very similar to the previous one, but I wanted to show you because it has radian measure, so you know what to do. So this time you're not going to add 180, obviously. You're going to add pi. So you just go plus shift pi, and now you have your answer. So the correct answer is actually 1. They want it to the nearest 100, so 1.58. Okay, so we say approximately 1.58. And of course, remember, this is the result for this. We just use the calculator to help us get to this. So this is, I just want to make it very clear, this is not the answer for that operation. This is the angle, the answer for this quantity using this operation. Okay, so be very careful with those inverse tangent, inverse cotangent situations. All right, so here we have a compound operation, or more of a composition of two functions. So we have the tangent of the inverse cosine of square root of 3 over 2 So this is where you apply one function and that output becomes the input of another. This is called functional composition. All right, so here we take care of the innermost part first. So we're trying to find some angle, its inverse cosine. So as you know, it's going to be between 0 and pi. We're looking for some angle between 0 and pi whose cosine, that means x value, is square root of 3 over 2. And of course, we can see that that is going to be pi over 6. So we're going to say this is the same as the tangent of pi over 6. So now we're basically done with any inverse trig function. We're just going to find the tangent of pi over 6, which, as we know, it's easy because it's the sine of pi over 6 over the cosine of pi over 6. So sine of pi over 6, of course, is 1/2, and cosine is square root of 3 over 2. So this is just going to be 1/2 over square root of 3 over 2. One fraction over another. We know it's going to be the outer product over the inner product. So it's going to be 2 over 2 radical 3. The 2's will cancel out, leaving a 1. And we have 1 over radical 3, and of course we always rationalize our answers. So we're going to multiply by square root of 3 over square root of 3. We finally end up with square root of 3 over 3 as our final answer. All right, with this one, this 2 here makes a big difference. If it were just the inverse cosine of 1/5, it would be one thing, but here, because of the 2, we're going to have to actually calculate a double angle identity. So what we will do, we know that the inverse cosine of 1/5 is just some angle, right, between 0 and pi, whose cosine is 1/5, but notice here they want exact value, and we're not actually interested in the inverse cosine of 1/5. We're interested in the sine of twice that. So that's going to enable us to actually find an exact answer in the following way. So first we'll do a clever substitution. We'll go ahead and let theta be that inverse cosine right there. All right. So basically we know that sine of 2 theta, so this problem now, remember, we're calling this part, we're just giving it the name, we're calling it theta. So that just basically now becomes just sine of 2 theta, right? Which, if you recall from our identities, that's 2 sine theta cosine theta. All right, so now theta is some angle whose cosine is 1/5, right? Remember, if theta is equal to inverse cosine of 1/5, that means cosine of theta is equal to 1/5. So if we just go ahead and draw a quick little image here, we can see that because we're looking between 0 and pi, we know that cosines are positive in the first quadrant. So we're going to draw a situation in the first quadrant. We're going to draw an angle whose cosine is 1/5. Remember SOHCAHTOA, right? That means we know that cosine is adjacent over hypotenuse. So we're going to draw our angle so that the side adjacent is 1 and the hypotenuse is 5. Now remember, this is not a unit circle, but we're doing it using triangles here. All right, so we need to find out what this missing piece here is on the right side. We have to calculate that using the Pythagorean theorem. So let me just go ahead and just call it y. So I get 1 squared plus y squared equals 5 squared. So y squared equals 25 minus 1, which is 24. So we get y is equal to, remember here we're in the first quadrant, so the y values are going to be positive. So we're not going to say positive or negative square root of 24 as we normally would if we were just solving an equation. But because we have a particular situation here, we're going to say just the positive square root of 24, which of course we can break up as square root of 4 times square root of 6. So we have 2 square root of 6. So this value here now we know is 2 square root of 6. So from that picture we can see, well, we already know the cosine, but remember we also need the sine of theta. So we can see that sine, as you know, of course, so opposite over hypotenuse, is going to be for this angle theta, the opposite side now is 2 radical 6 and hypotenuse is 5. So we're going to get 2 radical 6 over 5. Now we're ready to go ahead and calculate sine of 2 theta, which, by the way, do keep in mind that that's exactly sine of 2 times the inverse cosine of 1/5 that we're really interested in, because that's what we're trying to calculate. And remember, we call that theta. So basically it's going to be 2, we know that the sine of theta now is 2 radical 6 over 5 times 2 radical, don't forget there's another 2 radical 6 over 5 times the cosine of theta, which of course we know is 1/5. So now we end up with 4 radical 6 over 25, and we are basically finished with that problem. All right, so that's a really good problem. Make sure you understand the different aspects and that you can carry this on your own with no help needed. All right, so here we have another situation. So notice, instead of just having one angle, we have 2, so no big deal. We will go ahead and give them 2 names. So for example, we can let alpha be inverse tangent of -4/3, and we can let beta be the inverse tangent of 8/15. And of course, remember, if alpha is the inverse tangent of -4/3, that means the tangent of alpha must be -4/3. So tangent of alpha equals -4/3. And on this side, we must have that the tangent of beta is 8/15. So now we need to come up with some results here, but first let's go see exactly what results we need, because now remember, now that I've called this expression here alpha and this expression here beta, this really just becomes the cosine of alpha quantity, of course, the cosine of quantity alpha plus beta. So that's the cosine of a sum. If you recall, that's going to be cosine alpha cosine beta minus, remember the plus there requires a minus here, sine alpha sine beta. So what we need is the cosine and the sine of both alpha and beta. So we're going to obtain those from triangles again. We could use identities, but triangles are very quick. We can just go ahead and make one triangle here. Now remember, arctan is going to have outputs in quadrants 1 and 4, so we're looking between -π/2 and 2π/2 to set up an angle whose tangent is negative. Of course, in this region from -π/2 to π/2, angles whose tangents are negative fall in the fourth quadrant. So that's where we're going to set up that one. So I can probably do better than that. Let me try it again. All right, let's see. All right, not much better than that, but slightly. Okay, so remember in this quadrant, the y is going to be negative and the x is going to be positive. So we know this is sine over cosine, so we can set it up, or actually don't think that way, think opposite over adjacent, basically. So toa, right? Tangent is opposite over adjacent, so the opposite will be -4 and the adjacent will be 3. Now we know that this triangle actually should look more like this. That's a little bit more accurate. Okay, I'm starting to obsess over this a little bit. I get that way sometimes. All right, so we should recognize this. Two legs of a triangle, ignore the negative for the time being and just think of the lengths. Two legs of a triangle are 3 and 4. That means the hypotenuse must be, you said it, okay? That's a famous 3, 4, 5 Pythagorean. If you don't know that, of course, you can always solve it. Remember, when we want to set up the Pythagorean, we don't need to worry about the negative because we're interested in the length. So we have 3 squared plus 4 squared equals this is usually called the resultant, or r squared. So we get 9 and 16, 25 equals r squared. So r equals 5, obviously. Remember, this is the distance from this point to this point. This r is always considered positive value. So now we will be able to answer both sine and cosine for alpha. Remember, alpha is this angle in here. So we know that the sine of alpha is going to be opposite over hypotenuse, so -4/5, and that the cosine of alpha is going to be adjacent over hypotenuse, so 3/5. When we do these, at any point where you feel like, okay, you know, I got this, I'm just going to do this on my own and finish it, that'll be the best thing for you to do. That's how you learn mathematics, with engagement in the process. All right, so we're going to do the same thing now for the other one. You should definitely pause and do that on your own. All right, so assuming you're back, we're going to set up now an angle beta whose tangent is 8/15. So in other words, some angle between -pi/2 and pi/2 whose tangent is positive. So that means it has to be here, because here tangents are negative, so it can only be here. So 8/15 opposite over adjacent. So 8/15. You may recognize that. That's another famous triple. 8, 15, 17. You can go verify it for yourself if you like. All right, so this tells us that if this is beta in here, we know that sine of beta is going to be opposite over hypotenuse, so 8/17. And the cosine of beta is going to be adjacent over hypotenuse, so 15/17. Now we're good to go because we have all the pieces that we need, because we needed the cosine and sine of both. So now we just plug in cosine of alpha right here, 3/5 times cosine of beta, 15/17, minus sine of alpha, (-4/5) times sine of beta 8/17. So basically we get 45/85. The two negatives make a positive, so plus 32/85, which of course is going to be 77/85. And that's all there is to it. So just no panicking, you know, just set up different triangles, and that's as simple as it gets. Keep your quadrants in mind, because that's where how you, based on these, that you're going to set up your triangles depending on what the inverse trig function is. And that's it. You should be good to go. Let's go look at another one. We're almost finished, just so you know. All right, so here this one is just going to be an algebraic expression. They're not giving us any numbers, so this is going to be very algebraic looking once we approach it. So firstly, we're dealing with an inverse tangent. Let's go ahead and call that theta. So let's go ahead and let theta be the inverse tangent of u, right? So what does that mean? That means the tangent of theta must be u, which we can of course write as u/1, right? So that we have a quotient, we know how to form a triangle. So now we're going to go ahead and form a triangle. Remember that inverse tangent is defined in the first and fourth quadrants, from -π/2 to π/2. Now this u could be in either one of those, so we can actually set up two triangles here. So we can have theta here, or we may have theta here, depending on whether u is positive or negative, right? So if u is positive, it'll go up here. If u is negative, it'll go down there. But in either case, we know that the adjacent side, this is opposite over adjacent. We know the adjacent side is 1 in either case. So, and of course we know that when we want to use the Pythagorean theorem, it doesn't matter what sign, because we're just going to use the lengths. So we're going to have this hypotenuse is what we're finding, this r that we usually call it. So we have u squared plus 1 squared equals r squared. So we have u squared plus 1 equals r squared. So this means r must be the square root of u squared plus 1. So now we know what that length is. Let me just go ahead and just type it in. So that's going to be square root of u squared plus 1. So remember that we want the sine of this angle theta, because we called arctan of u theta, right? So basically we're interested in sine of theta, correct? So now look, sine, regardless of whether it's positive or negative, sine is going to be, sine of an angle is opposite over hypotenuse, right? So that's going to be u over square root of u squared plus 1. Just remember, we don't leave answers that are not rationalized in the denominator, so we're going to go ahead and do that. So we're going to go ahead and multiply the top and the bottom by the square root of u squared plus 1. And we end up with u times the square root of u squared plus 1 over u squared plus 1. And that's it. There's not much else we need to do, and this will work whether somebody wants to calculate this for a positive value of u or for a negative value of u. So what we did was very universal. Okay, and that's that. They just wanted the algebraic expression that represents this quantity in the variable u, and that's exactly what we have obtained. All right, so again, make sure that you can handle that on your own before we proceed. Okay, we've finally reached our last problem of this video. You must be thinking, yes, all right. Well, me too, believe me. Okay, so as usual, we're trying to write this as an expression, and as we have been doing, we're going to go ahead and give this inverse sine a name. Let's go ahead and call that theta. In other words, theta equals the inverse sine of u. So that means sine of theta must be u. Now, before we actually proceed with setting up triangles and whatnot, let's see if we even need to. If you recall, we're trying to find the cosine of 2 theta now, right? We had 3 forms for that. Do you remember? One of them was cosine squared theta minus sine squared theta. Then we manipulated that and we ended up with another form, which was 2 cosine squared theta minus 1, and a last one which was 1 minus 2 sine squared theta. Here we should definitely say last but not least, because if we want to use either one of those two, we're going to have to set up the triangle and find the missing sides, etc. But notice, if we want to use this one, we already have exactly what we need. So that's in fact what we're going to do. So we're going to say that cosine of 2 times inverse sine of u is going to be the same as cosine of 2 theta, because we're calling this theta, which is going to be 1 minus 2 sine squared theta, which of course does mean sine of theta and then squared. And we know what sine of theta is. It's u. So it's going to be 1 minus 2u squared. And that is as simple as that one can be. Of course, you could have gone with these others and you would have had to do a lot more work, but you would get to the same answer. So again, that's great practice to try to do that and see if you get that. All right, and that should do it for this video. We learned quite a bit. I know that it was a long one, but we needed it to get all the real details covered. So be safe until we meet again.